Okay, welcome back. This video is going to deal with multiplication of two fractions. Just like before, we're going to look at a word problem, and then we'll do the Cuisenaire rod and the area model, and then look at an appropriate paper and pencil algorithm that goes along with it. Again, when you do the word problem, you need to look at its structure, and so we're looking for something in the word problem that is multiplicative, and this is usually a little tough to recognize. It's an action that requires taking a portion of a portion. It's actually the same action that's involved when you're even thinking about a fraction like 1/3. It's multiplicative in the sense that 1/3 means take the whole, divide it into 3 equal pieces, and pay attention or do something with one of them. In this case, we're going to apply that multiplicative action to another fraction instead of to the whole. We will distinguish that between that and the subtraction, because with multiplication we're taking a portion of the portion. It's like taking 2/3 of 3/4 or 3/4 of 2/3, but with subtraction it's always taking 2/3 of a whole cup. So this is often confused with subtraction, and we will try to do a comparison so you can see the difference, because that's where students have typically the most trouble. So here's a word problem. Notice a little X alongside this top one. It shows this is a multiplication problem. Joe has 3/5 of a whole pound of chocolate. He gives half of what he has. Notice that what he has is 3/5, so we're really taking half of the 3/5. And the question is, well, how much was that? Because I want to know exactly what the answer to half of 3/5 is. So you ask, how much chocolate did Sue get then? What is the half of the 3/5? Notice it's very similar to the construction of a subtraction question. Joe has 3/5 of a whole pound of chocolate. All that's the same. The recipe calls for half of a whole pound. So the big difference is it's not half of what he has that he's given to somebody. It's half of a whole pound in subtraction. And then you always want to ask how much is left if it's a takeaway kind of subtraction problem. So here's the word problems again. We've already said this a little bit, but notice that what Sue gets is actually half of the 3/5 pound. Notice also, this is going to be really important in the modeling, that although multiplication in general is commutative, all that means is it'll give you the same answer if you reverse the order. But the operation here, the action that you take, is not commutative. It's not the same to give half of 3/5 as it is to give 3/5 of a half. So it's not commutative in the sense that the action would be the same. And so we have to pay really close attention with multiplication to make sure that the action is representing exactly what happened in the context. With subtraction, there's the problem again, but note that what Joe has left as a result after a half of a whole pound is removed from the 3/5 pound. So again, it's subtraction is operating on the whole. It's half of a whole pound. Multiplication is taking half of what was there to begin with and trying to figure out how much that is. So same format as before. There's the problem again. We're going to make a wall. Of course, that wall is going to have fifths and halves because that's what the problem is involving. We need to know what fifths and halves look like, although in this case it's not really half of the whole. So you'll see there's a little bit of a barrier, can cause some confusion for kids with multiplication. We're going to act it out, do exactly what the problem says to do, and then we're going to measure in some way and try to count and see what that is. So we'll start with the Cuisenaire rod model. I know the picture is up there. But we need a whole that has both fifths and halves in it. I'll explain later why that's really important. But here's the wall that we would make. Let me get it moved over to the document camera. So there is the wall. And again, it doesn't matter exactly what order this is in, but this is showing the wholes. This is showing the fifths because it takes 5 to make the whole. This is showing a half, and these are showing the little blocks that we're going to use to measure to make that up. Now notice that this is the same wall you do for addition and subtraction, and this is half of the whole, but this problem is not asking us to figure out half of the whole, so we have to be really careful. to not use this. Now, some people say, well, why don't you leave it out of the wall? Well, it turns out if you don't put it in the wall, you may have trouble modeling the rest of the operation because the hole needs to be big enough that it's got halves and fifths in it in order for us to even take a half of the 3/5 that we had. So there is the wall. We're going to act out the situation, again, using a linear approach. Notice that we have from here to here is the 3/5 pound of chocolate that we start with, but we want to give somebody half of what we had. So we have to go search for another rod that actually divides this 3/5 up into 2 equal pieces. So this lime rod here is actually half because it takes 2 of those to make up the 3/5. So this is a half of the 3/5. In fact, if you were drawing a picture, you'd probably actually even write that in there. It says this is 1/2 of the 3/5. A little hard to see that. Half of the 3/5. It's not a half of the whole. Notice the yellow rod was half of a whole, but this problem didn't ask us for that. And then we just measured to see how much this half of the 3/5 was. That's 3 little pieces. How big are those pieces? Well, you go back to the wall again up here to see that those were tenths. So this is 3/10 when you do half of the 3/5. So we've talked about not using the yellow wall. It has distraction, yellow rod. It has distraction potential here, but it needs to be in there or the wall may not work when we try to model this operation down here. So there's, if you look at the PowerPoint, there's what it looks like when we're modeling, finding half of 3/5. Notice that we weren't starting with a half and trying to divide it into 5 equal pieces and take 3 of them. That's what it would be if it was commuted. So the action is not really commutative. Okay, so what about the area model? So again, we're going to draw the whole unit. We're going to subdivide it to see the fifths. And probably not the halves yet, but since we have 3/5, we want to know what 3/5 looks like. And then we're going to shade and show that action and count. So let's start with drawing the unit. Again, it doesn't really matter, but a pound of chocolate might look like this rectangle here. And Joe has 3/5 of a whole pound, so we're going to divide this up into 5 equal pieces. And notice that Joe only has 3 of those. So Joe does not have any chocolate out here. This part is invisible. It's just showing what the rest of the whole would look like. We only have this much chocolate. And then what we're doing is giving a half of what he has to Sue. So how do you take a half of anything? You divide it into 2 equal pieces and focus on one of them. So, and the order here makes it a little bit different, but I'm going to try to model this exactly the way that, exactly the way that the action would happen. We're going to take the chocolate we have here and divide it into 2 equal pieces. And I know that this piece right here, I'm going to circle it and point to it and say exactly what it is. Move over just a little bit. This piece right here is 1/2 of the 3/5. And so it is 1, 2, 3 pieces if I were counting. The problem is I know the answer is 3 somethings, but I don't know what they are until then I go back with the rest of this wall and continue the shading out here so I can see all those pieces the same size and notice, oh, those were tenths. And so when we're done here, we really are getting 3/10 for an answer. So see how it's half of only the 3/5 that we had. Divide the 3/5 we had into 2 equal pieces. Pay attention to that. Count to see how much it is, but you'll have to make the whole unit into those same size subdivisions so you can tell if those are tenths. So we made the unit, we subdivided to see the fifths. We're waiting to do the halves until we operate on it. So we shaded the half of that if you're looking at the PowerPoint now. And so now we're ready to look at the paper and pencil algorithm associated with this. And I'll just remind you again, let me go back. Just remind you that paper and pencil algorithm should come late. It should come only after you've already done quite a bit of activity with materials so that the kids really have internalized exactly what it takes to be multiplicative, what kind of word problem structure it takes, what do the operations look like at a very concrete level so that it really makes sense what it means to do when you're taking something like a half, a 3/5. And once that's all in place and they understand it well, then you can say, well, let's just kind of keep a record of what we've been doing so that we don't have to make these pictures all the time or don't have to do the walls eventually. We can avoid the Cuisenaire rods and stuff and just do it with an abstraction with the paper and pencil algorithm. So make sure the paper and pencil algorithm comes sufficiently late. If you do it too soon, the focus just becomes on manipulating the numbers and the concepts won't necessarily be developed, or there won't be a connection between the paper and pencil algorithm and what was done at a very concrete level. There won't be a conceptual connection. So assuming that we've done all that, we're ready to move forward and look at what a paper and pencil algorithm will look like. We'll start with the area model since it's up here, and it's actually usually the most easiest to see here. So it's going to look something like this. We're really trying to find 1/2 of, which we can do as a multiplication, of 3/5. And what really happened is we changed the 3/5. We gave the 3/5 a different name. I'm really trying to take half of 3 objects here. I know that little circle's not shown in the PowerPoint because you can't do anything with that other than you say, well, half of 3/5. I know that's 1.5 fifths, but generally you wouldn't want to leave it as that kind of answer. 1.5 fifths is kind of a strange answer. So what we do is change this 3/5. We're still trying to take half of something, but the 3/5 actually became, if you look at this, 6/10. And now if I try to take half of 6/10, we've written an equivalent fraction for 3/5 so that it actually is possible to take half of that 3/5. But now it's 6/10. I know what half of 6 is. These tenths are objects just like apples. A half of 6 apples is 3 apples. Half of 6/10 is 3/10. So we know the answer is 3/10 here because of where the operating is happening. This 10 down here is kind of just a placeholder. It's an object. It's the name of the object. They happen to be called objects like tenths, which is one of those initial ideas that is probably a prerequisite before we're doing this, that kids develop meaning of fractions so that something like 2/5 actually does mean 2 of these fifths. Those are just objects. Okay. And let me point out that that algorithm is still involved back here in the area model. In the Cuisenaire rod model. If you look at the 3/5 here, you can actually tell that 3/5 has an equivalent name of 6/10. And so half of that's clearly only 3 of those. And it shows up again when you do the operating down here. Do the operating, you can see the half of the 3/5 is actually half of 6/10. 3/5 is still 6/10. Half of that's going to be 3 of those. So the algorithm that fits this is actually not what you're used to doing with multiplication of fractions. You've been taught to multiply straight across, and it actually works. But if you ask people why does it work, they just say, well, that's what I'm supposed to do. It doesn't have any meaning. Turns out that if you're trying to do curriculum so that it's conceptually meaningful to kids, you want to make sure that your abstractions, your paper and pencil algorithms, are as closely matching to the concept that they developed. And the concept as we developed it here was not a multiply straight across. There was no such thing with Cuisenaire rods. How would you multiply Cuisenaire rods straight across? I don't even know what that means. But what really happened was that we got an equivalent fractions algorithm. We changed that second number to a number that was possible to operate on. Half of 3/5 I don't like, even though I could answer 1 1/2 and that would be conceptually meaningful, but not the form we like to put it in. But I know that half of 6/10 is 3/10, so we just changed it to an equivalent fraction. Okay, so let's try a second one. So here the word problem is Justin has 2/3 of a whole quart of ice cream. He really likes Cindy, so he wants to give her 3/4 of all the ice cream he has. The reason we're doing a second one here is because we wanted to try to model one where we didn't have unit fractions all the way through. Sometimes unit fraction ones are a little bit easier to model, and so we're taking 3/4 of what was there. So he's giving Cindy 3/4 of the ice cream he has. So we're really taking, as you can see here, 3/4 of the 2/3 quart. So we're solving 3/4 of 2/3 and not the other way around. We're not really starting with 2/3 of a whole quart and giving Cindy 3/4 of what we had. I mean, that's a significantly different picture if you tried to model it. So again, we will do the Cuisenaire rod. Cuisenaire rod model will make the wall. We will act out the situation. In this case, it's a linear approach again because Cuisenaire rods are linear, more like a number line kind of thing, and then we'll measure that. So let's start with the wall. So here's a wall that shows the hole. Notice that since it requires a unit that has 12 in it in order to have both thirds and fourths, that's least common multiple stuff that you might have picked up in your number theory work. To have thirds and fourths, it's got to have 12s, but notice the standard Cuisenaire rods do not have a 12 rod. So we had to put it together, and a 10 and a 2 is what most people use. So there is the one that shows everything. Now, this is not a standard Cuisenaire rod, but what I've done is made a unit that is it's just slightly too long. I need to take it back to the table saw. But now I've got a single rod that really represents that whole unit, and it really is a 12 rod. That might be better if we had a rod that was all the way across, and for some virtual manipulatives you can find sometimes you can find Cuisenaire rods that will or alternatives to Cuisenaire rods that will allow you to make a single unit that's a 12 rod. Sometimes having two pieces will confuse kids because the hole isn't quite as clear when there's two pieces involved. So we'll leave this here as a single unit and then model the rest of it. So then we're going to act out the situation. So again, Justin has 2/3 of a whole quart of ice cream. So since these purple ones are the thirds, there's what Justin has. And he likes Cindy, so he's not going to give it all to her, but he is going to give her more than half. So he's going to give her 3/4 of all the ice cream he has. So notice that it's not these fourths right here because these are fourths of the whole. We need fourths of the 2/3. So we have to go find another rod, and again, it's experimenting. You just have to go find something, but eventually you'll get to the point where you can do this fairly quickly. And notice that those are the rods that divide the 2/3 up into 4 equal pieces, and I want to measure only 3 of those because I'm interested in 3/4. So if I just measure that many, that kind of indicates I'm only measuring up to here. And measure with single blocks, that's 1, 2, 3, 4, 5, 6 pieces. And how big are those pieces? You compare back to the wall again. Those are 12ths. So I know it looks like a funny answer when you're done, but the answer to this really is 6/12. And I know the question we did on purpose, so you can think about it. Well, should you simplify that or not? And I know that the Common Core people have made less an emphasis on trying to simplify stuff. 6/12 actually makes more sense here because it's the way it was generated from the model. to get 1/2 out of this, you have to do a little bit of work. But 6/12 is just fine for an answer, and so I would say at least initially leave it that way, because that shows how it was developed based on the way we did the model. Now, again, the thing that are going to trouble kids most often is that you had to go find a different rod here that wasn't in the original wall. That's what's different about multiplication than the rest of it, because we don't want force of the whole, we want force of the 2/3. Okay, so we'll go with an area model next. So Justin has 2/3 of a whole quart of ice cream, so we're going to draw a whole quart of ice cream. And Justin has 2/3 of the quart, does not have any ice cream out here. So again, we're going to draw the whole unit, and then we're going to subdivide to see thirds and consider how to find force of that. Well, how do you find force of anything? Well, it's based on the concept the kids already have. They know that 1/4 is a concept in action. It tells them what action to take. You take whatever you have. If it's a whole, you do it with a whole, but here we only have 2/3 and we want force of that. So how do you find force of anything? You divide it into 4 equal pieces. And I want 3 of them. So there's what I'm interested in finding. And that is actually 3/4 of, I'm going to use the of there, of 2/3. That's a 2. And so it is 1, 2, 3, 4, 5, 6 pieces. But how big are the pieces? Well, we can't tell until we finish the subdivision out here. Notice we didn't have any ice cream out there, but that tells me that there are 12 pieces in the whole. We have 6 of them, and so 6/12 is a good answer, and it reflects what we actually had there. So it makes sense that I can't use the ice cream out here, and so when I take 3/4 of the 2/3, it's only the 2/3 that I'm dividing up into 4 equal pieces and taking 3 of them. So there's the model on the PowerPoint. Looks pretty much the same. I would add that little notation. If I were taking a record of this, I'd add this notation over here, this 3/4 of 2/3, to say that's what that really is. So that's why that makes sense. That's what we're finding, is 3/4 of the 2/3. So what about the paper and pencil algorithm? Again, it should grow out of the material work. So let's see what happens here. So the sense we've already made of it, we're just going to record that. And so if you look at the algorithm, we were originally trying to find 3/4 of 2/3. We are not going to change the first fraction because that's our multiplier. We don't want to make it any more complicated than it is. But we are going to change the 2/3 to its equivalent name, and notice that 2/3 up here became 4/8/12. So this now becomes 3/4 of 8/12. And why that's an advantage is because I don't really like taking 3/4 of 2, although I could do that as 1.5. 1.5 thirds may make sense, but I don't like it. But when I change the 2/3 to 8/12, I can take 3/4 of 8/12, so it's a little bit more complicated. What I would normally do is think, well, what's 1/4 of 8? Well, 1/4 of 8 is 2, and so 3/4 is going to be 6. So I know the answer is 6, and this object right here, it tells me the kind of objects I'm talking about. They are called 12s. So you notice again, there was not a multiply straight across. There was an equivalent fraction where I'm getting equivalent fraction between 2/3 and 8/12. So they're the same fraction, so I just rename it so that I can actually do the operation a little bit more clearly. And if we did the Cuisenaire rod model, I can maybe get the wall back up here again. You can see again that the 2/3 here actually becomes 8/12 if you look at it up there, and so I can take force of that 8/12. So the algorithm is not a multiply straight across. it is an equivalent fraction kind of algorithm. By the way, when I show the algorithm, I think that little circle on there that shows where the operation is actually happening is very important because that shows the concept. I've already talked about that 6/12 makes sense because a fourth of 8/12 is 2, and so 3/4 will be 3 times as much, and I just leave it that way. There's no need to simplify it. So here's just a few notes on multiplication. Again, it's nice to encourage estimation. And then compared to the exact results. We know that the answer here of 6/12 pretty close to a half. We should expect an answer pretty close to a half because we only started with 2/3. It wasn't quite a whole. Started with a little bit more than half, and we were taking most of that. So starting with a little bit more than half and taking most of it kind of makes sense. We should end up with an answer around a half, and you want kids thinking about that as they're going through this process. It's always good to say, before you actually model anything, what do you think the answer is going to be about? How close would it be? For the Cuisenaire model, let me get that one back up here. For this Cuisenaire rod model where we're doing 3/4 of the 2/3, it is extremely important that all 4 of these blocks are shown in here. Some people will say, well, I don't need that one in there because I'm not measuring it. But the question would be is, well, then what does this block represent right here? And the kids might say, if they really know the answer, know what they're doing, they might say, well, that's 3/4 of the 2/3. I say, well, how do you know it's 3/4 of the 2/3? And they will immediately put this back up here and say, well, because it takes 4 of them. Well, if that was in there to make sure this was 3/4, it ought to stay there as a very concrete model. So I would encourage you with the kids to have them leave this here because otherwise it isn't clear that it takes 4 of those to make up the 2/3. And so I don't really know that this is 3/4 of the 2/3 if that part's left out, although it looks like it. This makes it absolutely concretely clear that that's the case. And then the next thing with Cuisenaire rods, if you'd started with more than 1 unit, in other words, suppose he started with 1 2/3 quart of ice cream, how do you do that? Well, let me show you very quickly with an area model on that. And you do the same thing with the Cuisenaire rod models. You just add a unit to what you had. So you have 1 2/3 whole quarts of ice cream. So there's the first quart of ice cream. You have all of that. And you have the second quart of ice cream. And you only have 2/3 of that. Nothing out here. Apologize for making that a little sloppy there. But there's the amount of ice cream that we have. We don't have any ice cream out here. And then if you want to divide that into 4 equal pieces so you can take 3/4 of what was there, you divide the 1 2/3 into 4 equal pieces. And we're interested in 3 of those if we're doing 3/4. So that's what we're interested in counting here, is this piece that is 3/4 of 1 2/3. And then you just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 pieces is what Cindy is going to get. But how big are those pieces? Well, just like before, those pieces are 12ths. And so an answer of 15/12 does make sense. Now, the kids will, again, can get trouble with this, but you got to recognize that that's the whole quart. And when we say 15/12 or 1 6/12, or sorry, that would be 1 3/12 for the final answer here. That means 1 whole quart and 3/12 more. The unit has not become 24ths all of a sudden. That can be a little bit of a barrier. So you just adjust and make the unit bigger. Put a whole unit out front and do the rest of the operation just like you normally did. If it were Cuisenaire rods, you'd put 1 2/3 down there and then go find this other rod that divides that up into 4 equal pieces just by searching around. We talked about this before, but for Cuisenaire rods, it's better not to use, not to destroy the wall because we need to keep referring back to it to knowing what the hole looks like and how many little pieces are in the hole. We talked a little bit about the half of 3/5 we could have done as half of, like half of 3 apples is 1.5 apples. So you could answer 1.5 5, but it's better to go ahead and change that to something you can operate on, that we give an answer that we're a little bit more comfortable with, like 3/10, because 1.5 5 bothers some people. For multiplication, we've kind of skipped over some of the kind of problems that will have been done initially, but I want to make this absolutely clear that when you have a problem, something like 1/3 of 3/5, so we're trying to take 1/3 of those 3 objects that are called fifths, that should be conceptually clear without having to do any paper and pencil, without having to do an area model or a Cuisenaire rod model. We know 1/3 of 3 apples is 1 apple, so 1/3 of 3/5 is 1/5, and so there's nothing to do on that one. So we've purposely jumped to the harder problems so that you get to something that actually requires that you do some kind of modeling to figure out the answer. It is a matter of power that you want to develop with your students, that they recognize when there's a problem that's been presented to them that they can just think about and know the answer without having to just go through some kind of mindless set of procedures, either with paper and pencil or a mindless set of procedures with area model or with Cuisenaire rods to find an answer. So something like 1/3 of 3/5, we want them to say, oh, I know the answer to that. I don't have to do anything else. Now, if they happen to have written it down like a paper and pencil algorithm, if it's something like 1/3 of 3/5, and we're used to this idea of saying, I'm interested in operating there, well, that's already in a form that I know 1/3 of 3. I don't need to do anything with that. 1/3 of 3 is 1. So obviously the answer is 1/5. But we just don't want to have a paper and pencil algorithm to get there. We want them thinking about that and using that good brain that they have, and always looking for things that make sense to them rather than just letting their brain just run off and follow these pathways that have been developed for something else. It's a power issue. Okay, so a couple more notes here. The equivalent fraction paper and pencil algorithm. I made a big deal about that this is not a multiply straight across. Notice, though, that even this new algorithm can lead to a potential mental arithmetic. It's kind of like visualizing the paper and pencil algorithm, but at least it's conceptual. 1/3 of 2/5, I have no idea what 1/3 of 2/5 is. I don't like taking 1/3 of 2. But I know that 2/5 has some equivalent names. 2/5 is 4/10, but 1/3 of 4/10, I don't like that. 2/5 is also 6/15. 1/3 of 6/15, yeah, I can do that. 1/3 of 6/15 is 2, because 1/3 of 6 is 2. So it's 2/15. I can figure that out by kind of in my head thinking through what the paper and pencil algorithm would have looked like if I had done it with the materials and thinking about an equivalent fraction algorithm. So it can lead to some mental arithmetic that you don't have to do the materials, don't have to model it anymore. Now, the other thing that can happen is the child may eventually discover that you actually can get the same answer if you multiply straight across. And I'll just say that that's nice if they see that. I, as a teacher, would never, ever tell them that, because the minute I tell them that, it short-circuits the whole process. They're not near as interested anymore about why does it make sense that I do that, because you're going to have trouble explaining why it makes sense. So how are you going to deal with that as a teacher is a kind of a dilemma, because they will recognize it. They may have even been taught it in a different class before. But you always want the abstractions, the mathematics that they're doing, even if it's at the paper and pencil level, you always want to be able to treat those as symbols so that you can unpack them and see what does it really mean and where does that come from, why does it make sense. Otherwise, it's just a mindless rule, and then the kids will forget which rule do I apply with which operation, and then math just turns back into something that doesn't necessarily have to make sense. However, if the kids notice it, and you have already developed it, what this multiplication of fractions means at a concrete level, I would say, well, that's really nice that you notice that. You know, as long as you can always go back and show me what multiplication really looks like, go ahead and use that shortcut if you want to. But I wouldn't do it too soon. And one way to avoid doing it too soon in some cases is to avoid telling the kids that shortcut, because we're not doing the math so we can get an answer. If we just want an answer, we got a fraction calculator that'll give them an answer without them having to do any thinking about it at all. We want them to understand where they've been going here. So, so try to avoid that jumping to that shortcut multiply straight across algorithm. But if they get there, it's not a big deal. Now, the other thing I will say is that if you look in some of the Common Core progressions documents, there have been attempts there to try to make sense of the multiply straight across algorithm, and I'll leave it up to you to see if when you look through that material, whether or not that makes enough sense that you think kids could follow. My personal preference is to start at the extremely concrete level with area model and Cuisenaire rods and have the kids see that there is at least an algorithm that represents what they've already been doing that is not the multiply straight across, and it does make sense. I'd rather everything that they do make sense. Oh, there's a note here about if you ever have to draw these, like for an assessment or something, please make sure the kids know that for the Cuisenaire rods, they must put the model down first. You don't want them guessing about what the model would look like and drawing it without actually putting it down, because it kind of also short circuits the relationships that are very clear at a conceptual level when you're actually using the rods. A couple more notes. Some have actually argued that the understanding of the fraction itself as an action, we've talked about this already, that 1/3 actually means to take the whole, divide it into 3 equal pieces, and do something with one of them. And that's exactly the operation you do when you're doing multiplication, that you're taking whatever you're starting with, it might even be 2/3 or something, and if you're taking 1/3 of that, you're going to take the 2/3, divide that 2/3 up into 3 equal pieces, and pay attention to one of them. That's essentially the idea of what the fraction means as just standing alone. What 1/3 means as a fraction. And so even though I don't normally do this, some people have argued that you could start teaching multiplication of fractions even before you do addition and subtraction. Sounds a little strange to do that. That's just an issue for you to think about as a teacher, whether or not you would feel comfortable doing that. Just something somebody's noticed. Also mentioned this multiply straight across in the Common Core. You might look at that. They have some alternative views about fraction development. I'd like you to at least see what we've done here with this concrete modeling and compare and contrast that, see what you think. Try some things with kids, see what the kids would do. Just know that there are alternative ways of doing some of the things that we've been doing here. You ought to pay attention to that. Also, I'll mention that there's a group out there called the Rational Number Project, and they for quite a while have focused on circle models and have done circle models to do at least some initial fraction things and even carry that up into some of the operations. That's something you ought to look at. I mean, personally, I think that the area model is more powerful because it's really two-dimensional. Circle is two-dimensional, but when you make the subdivisions, they're all coming out from a single point, and so in some sense it's one-dimensional because you can't really see thirds and halves easily at the same time. But just know that there are other alternative approaches out there that you might want to consider and try and see which ones work best for you. Number line model is also another one that's showing up in the Common Core quite a bit. I think that the Cuisenaire rods would grow nicely into a number line model, and I think they're a little bit more concrete. Sometimes with a number line model, you kind of have to know the answer ahead of time before you get it. At least that's my opinion, but I want you to have considered that there are alternatives that people have suggested, and wouldn't want you to just discount those. Okay, so that's the end of the multiplication one. Again, I'll remind you that that you should consider, since the video is long, you probably, I hope you did this already, but take it in short spurts, but go back and review anything that you need to, that you have trouble with. On all these videos, you should be, I know this is telling you after the fact, but all these videos you should be thinking about getting materials out, actually drawing area models, actually getting Cuisenaire rods out and seeing how those work. Okay, thank you.